Hi everyone. Can you hear me fine? Is the sound good? Okay. Welcome everybody to my talk. Protobuf all the things end-to-end gRPC service architecture. Last day, last hours. So like, bear with me while I go through this. So, who am I? My name is Valerio Versace, and I am a software development engineer at Ocelot Technologies, which is a Seattle-based technology company that is working on solving the infrastructure problem. What is the infrastructure problem exactly? We'll get into that later. It will be more evident as I go through the talk. I'm also CTO and founder of Soluzioni Futura, which is a company based in Italy that does consulting in the cloud and software development space. So yeah, this is the rundown. What am I going to talk about today? Today I'm going to show you how to build a service platform using gRPC as the framework for communication between services and between clients and services. But it's going to be a decentralized service platform, meaning that it will have no central point of failure, and it will be censorship resistant, as they say nowadays, meaning that no central authority can decide who gets on the platform and who doesn't, and it's impervious to government shutting it down or whatever. So, fun fact, as I was going through the talk yesterday, there's a bunch of technologies involved. We're gonna see them in a few seconds. And I went, okay, this is a lot. Like, there's some stuff that people in the audience might have not ever seen before. What do they do when they get home? Like, do they have anything to see, to kind of try to play with the technologies that I mentioned? And then I said to myself, this would be much easier if I had some code to show, right? Some MVP or something. So I checked in the hotel room and took out the computer and started hacking at the keyboard. So I made the MVP. It's the platform. I'm going to show it to you later. And it's something that you're going to be able to see on GitHub. And you can fork it. You can deploy it. You can play with it, like whatever. It's out in the open. You can do whatever you want with it. That was quite a piece of work. So what are these technologies that are involved that I'm talking about? Let's go and check them out. So gRPC, that's in the title. It's pretty obvious. It's a framework that was originally developed by Google to do remote procedure calls and to communicate between services and clients. We're going to get into that later. Has anybody here ever used gRPC? Like, how many of you have used gRPC in production? Okay, not too bad. How many of you know what gRPC is but have never used it? Okay, fine. Nice. Well, I hope after the talk you'll get more chance to play with it and see if it works for you. Then IPFS, which stands for Interplanetary File System, big name. How many of you have used IPFS? One, two people. Okay, that's more than I expected. So 2 people have used IPFS. How many of you have used BitTorrent? I'm not the police, so okay, nice. You weren't shy anyway. It's similar, meaning that IPFS is a distributed storage system that is based on the same mechanism as BitTorrent, meaning that it's essentially built upon a system that is called Kademlia. So yeah, there's some similarities with BitTorrent. Then Ethereum. How many of you have used Ethereum? Okay, nice. How many of you don't know what Ethereum is? No idea what Ethereum is. Okay, Ethereum is a blockchain like Bitcoin, but it's a little different from Bitcoin, meaning that the focus of Ethereum is not financial transaction, but rather decentralized applications. And we'll see what that means a little later. But you can think of it of something like we have this MySQL database that everybody has access to and that everybody can use and write to, only that you can only use the stored procedures. So you're going to write these procedures, which are called smart contract in Ethereum, and you're going to call the functions on those procedures to write data on the Ethereum blockchain. And then there's Lightning Network. How many of you know what Lightning Network is? Okay. Yeah, there's a bit of overlap, meaning that the people that used Ethereum have also used IPFS and they've also used Lightning, and yeah, that's expected. So let's start. Which one do you want to start first? I mean, it's going to be gRPC because the slides are in order, so you don't really get to decide. So gRPC. What is gRPC exactly? As I said, gRPC is this framework originally developed by Google to do remote procedure calls. Even though it's been originally developed by Google, it's actually open source, and there's a lot of people and companies that contribute to it. So yeah, it's completely open, and it's evolved beyond the original vision by Google. gRPC, you might compare it to something like REST, for example, or Avro, or Apache Thrift. The one that you're most probably familiar with of this bunch is going to be REST. So I'm going to explain to you what gRPC does for you by drawing comparisons with REST, because that seems like the easiest path to go. So gRPC versus REST. What's the difference between gRPC and REST? Let's start talking about REST. First of all, REST is not a framework like gRPC, but REST is actually an architectural pattern, meaning that you have way less conventions, you have way less formal specification, and in the wild, a lot of people are going to implement REST differently from each other, especially when they try to overcome some of the limitations that REST might have by design, so to speak. So the essence of REST is that REST maps HTTP paths and endpoints to resources in your application, and it maps HTTP verbs to actions that you might want to do on these resources, meaning that with REST, you might have a platform that exposes a /users endpoint that if you call it with a get method, it would return the list of users of your platform, whereas if you call the /users/ some kind of user ID also with a get method, it would return the information about a single user. On the other hand, if you called the users endpoint with a post method, you might be able to create a user in your application, while a post method on the single user, like /user/user ID, would allow you to edit information on that user. And the delete method would delete the user, I suppose. So this comes with some limitations, meaning that not everything maps well and cleanly and in an elegant way to resources and actions. Some things are just more suited to a remote procedure call kind of semantics. So there's a lot of discussion, like even 10 years after the fact, 12 years after the fact, whatever, about how to map certain actions and certain operations to REST. One such example might be, imagine that you have a platform that exposes an endpoint that takes an image and it identifies the faces inside that image. So you're going to give it an image, and maybe you tell it what type of image that is, like if it's PNG, base64 encoded, or if it's whatever. And what you expect to get in return is an array of bounding boxes with 4 coordinates, like top left, width, and height, that tell you where the faces are inside the image. Like, how are they going to map that to REST? Is it going to be like /faces in post, /image in post? In this case, it probably makes sense to have a resource that has the action and what you're doing with it. Another example would be like send email. Would that be like a /email endpoint that you call in post, or a login endpoint? Other limitations of REST is that it was born in the days of HTTP 1.1, so it doesn't fully leverage some of the constructs that were born later, essentially, with stuff like HTTP 2. It's tricky to do streaming with REST. I mean, actually, you can implement an endpoint that does whatever you want, right? But if you go with frameworks that allow you to structure your REST endpoint and that allow you to structure your REST applications and maybe generate code or generate documentation for your REST application, it's hard to find frameworks that, out of the box, give you the ability to specify streaming interfaces. The other thing is REST doesn't actually mandate a data interchange format for your application. You are free to use whatever you want. But in most cases, it's actually going to be JSON, which is fine. It's human readable. It's wonderful. Everybody loves JSON, more or less. But at the same time, as an encoding format, it's UTF-8 strings over the wire, meaning that it's going to be less efficient than trading binary data between services. So it's going to be heavier on the wire, and it's going to be slower to parse in whatever language implementation that you have. Another problem of REST is that, as it's not a protocol, but like a series of recommendations and constraints, it wasn't born with a way to formally define a machine-readable specification, but it's something that like people plugged in way after the fact using standards that were born just to do this. The example that you're all familiar with, or most of you will be familiar with, is OpenAPI with something like Swagger. How many of you here use Swagger? Okay, it's pretty a hefty number. The question is, how many times have you used a REST API that didn't provide you with a Swagger representation, and you basically had to read some like hacky documentation or try to figure out like what the resources were for that API? Show of hands. Yeah, okay, it's the majority of people. So I'm specifying this because a lot of time when I say this, people go like, oh, but there's OpenAPI and Swagger. Yeah, sure. But at the same time, with something like gRPC, where you have a protocol-mandated way to define machine-readable interfaces, you are 100% sure that every gRPC API you are ever going to call is always going to give you this machine-readable representation that you can use to generate clients, generate servers, and generate documentation. Whereas in REST, you are basically prisoner to the goodwill of people that write APIs or lack thereof. So how does gRPC solve the problem? gRPC employs a interface definition language that is called Protobuf. Protobuf stands for protocol buffers. And protocol buffers is a way for you to define services, to define the methods of these services, like what's the method name, what kind of request it takes, what kind of response it returns, and how it behaves. Like, is it a request-response pattern, or is it like a client-side stream, or a server-side stream, or is it bidirectional streaming? You're going to specify that in the interface representation. Protocol buffers is also the encoding format for the binary messages that you're going to exchange over the wire. It's very efficient. It's very compact. In size, it's pretty similar to PER encoded ASN1 messages, if you've ever used them. How many people here have played with ASN1? Okay, nice. How many of you have played with other formats like Corba or whatever? Yeah, okay, there's a few of you. Well, this is like you can use this instead of that. Actually, we're gonna like see something in a few slides that there's some possibilities to actually change the data encoding format that you use with gRPC. We'll get into that. So Protobuf, you're gonna take the interface that you wrote in Protobuf for the service, and using a compiler for protocol buffers, which is called ProtoC, you're going to be able to automatically generate client libraries and server libraries for 10 different languages. I don't remember them all on top of my head, but there's Java, there's Go, there's C++, there's Node.js, there's Python, there's Java Android, there's Swift. So you get everything you want, essentially. And these generated client libraries are going to encode the requests that you're going to write in your application using the native objects of your implementation language. So you're going to write JavaScript objects or Python dictionaries or whatever. And the libraries are automatically going to encode those in the Protobuf binary format for you. And the server implementation will translate your requests back to the native objects that your server is implemented with. And same when you give back the response to the client. So yeah, Protobuf has the binary wire format. It's going to be lighter on the wire, meaning that the size of a Protobuf binary encoded message is going to be much smaller than a JSON on average. Like, it depends. If it's all text strings, it's going to be similar. If it's like a collection of objects or integers, whatever, it's going to be much lighter. This is a Protobuf definition for a service. I wrote a horoscope service, a sample horoscope service that takes I'm looking at the screen because like in my screen it's impossible to read. So you have a horoscope service with a get horoscope method that takes an horoscope request and returns an horoscope response. I tried to look up what kind of protocol horoscopes use, like if there's an RFC for horoscopes to know what kind of information you have to provide to get back a prediction. Apparently, there's no formal specification for horoscopes, so I made up my own thing, which maybe is what the guys actually do, I don't know. So you're going to have a horoscope request that is going to take a zodiac sign, and you're going to have a horoscope response that is going to return you the prediction, like it's going to tell you the future. And yeah, it's all here, like there's nothing else. If you've written Swagger representations for like just a single get method, you know how much verbose they can be. Anything else? Like, does gRPC give us anything else, or is this it for gRPC? There's actually more. So gRPC has pluggable authentication mechanisms, meaning that you can do authentication in gRPC using whatever you want. You can use tokens, you can use API keys, you can implement HTTP basic auth, like gRPC doesn't care, and neither do I. Do whatever you want. I've done authentication on gRPC using all of the ones that I mentioned before, but I've also done authentication on gRPC using stuff like transaction receipts on the Ethereum blockchain or invoices in Lightning Network. Like, go to town. You can do whatever you want. Then it has custom serializers and deserializers, meaning that you have this huge old legacy application that is written based on JSONs or based on Corba or based on whatever. You don't want to rewrite all of the application logic or all of the data access logic. You can just do gRPC, and in the generated client libraries, you override the deserializer and the serializer and just put JSON parse and JSON stringify in there. And you're done. And then it has this concept of interceptors, both on the client side and on the server side. And what interceptors are essentially abstractions to write middlewares for your application. So you could write an interception that does automatic retry if the service is unreachable. You could write an interceptor that does exponential backoff on the retry. You could write something that goes to your external authentication system like LDAP or MySQL or whatever to fetch the credentials to authenticate itself with the server. You can do all that. And on the server side, again, same thing. You can implement whatever you want to work on the request or do logging or metering or like verify some strange kind of headers that you want to put in the request. You can do all that. It's completely open, and you can literally do everything with it. What's bad about gRPC? gRPC has horrendous browser support, because a lot of the HTTP2 proper constructs that it uses are either not implemented in the browsers or are not implemented in the kind of APIs that you will use in the browsers to make the requests. Meaning that fetch API in the browser doesn't support a lot of the stuff that gRPC is going to give back to you, so your browser is just going to crash or get stuck or whatever. And XML, HTTP request, XHR, same thing. There's ways to make gRPC work with the browser. I've done them. The two main ones are, number one, you write yourself or you employ one of the existing methods to essentially parse HTTP2 gRPC requests to HTTP 1.1 machine digestible, browser digestible requests. The other one is that there's tools, one of them developed by Google, that essentially write for you an API gateway that is REST-based for gRPC backends. So you're just going to be able to say, OK, services talk to other services using my gRPC interface. For browsers, I'm going to automatically generate the REST interface, and browsers are just going to use that, and they're going to point to the same backend services. So what are we talking about when we actually speak about services in the context of a microservice architecture or a service-oriented architecture? I'm not going to dwell on the semantics and the difference between the two because it doesn't matter. Services are independent application components that are loosely coupled to each other. So one can stay up, one can go down, different teams can work on them, you can scale them independently, and you can deploy them independently. These services are going to be black boxes to each other. They're going to be oblivious to each other's location, meaning that a service needs to be able to call another service just by name, and some other component in my architecture needs to be able to provide to the clients or the other services the information about where a service is, and maybe do load balancing. If you have like 10 instances of that service running on 10 different boxes, it's going to have to route the request to one of these. They're going to be oblivious to each other's implementations, meaning that my client or my other service doesn't need to know whether the service that it's calling, it's written in PHP, Go, Java. Doesn't have to matter. They're going to know about each other's interface, though, because if you need to be able to construct requests to a service, you need to be able how to call it, to be able to know how to call it and what endpoints it exposes and what kind of payloads they're going to take. So they need to know about each other's interfaces. And they're going to be communicating via message passing over the wire, meaning that in a monolithic application, you would have a single thing with all the business logic showed in, and everything is going to work in the same memory space, and functions are just going to pass objects to each other. In this case, you're going to communicate like either via inter-process communication, like Unix sockets, or most likely, if stuff is in different boxes, you're going to talk over HTTP or TCP or whatever. So back to the start. I told you that we would be making a decentralized service platform. And as I said, we're going to need some kind of service registry where we're going to save information about the services, like meaning where a service is and what its interface is, for other services to be able to call it. We usually would be putting this on some distributed system that stays in my data center. That's going to be something like, I don't know, Consul or an Nginx that uses an etcd or whatever, or it can be just like Apache redirection rules. In our case, that doesn't work because we want something that is decentralized, that is censorship resistant. So the thing that I chose to use is the Ethereum blockchain, and I wrote a service registry using an Ethereum smart contract, and we are going to use just that for services to advertise themselves to other services and expose the interface that other services and clients are going to use to call them. So what is Ethereum anyway, and why did I end up using Ethereum? Ethereum is a platform that is based on smart contracts. Smart contracts are essentially code that you deploy to this blockchain. The blockchain is a decentralized storage, and everybody can run an Ethereum node, just as you would be able to run a BitTorrent node or whatever. And an Ethereum node is going to have a whole copy of the whole Ethereum blockchain, meaning every transaction that has ever been run on the Ethereum blockchain, and meaning all the data that is written on the Ethereum blockchain. So it's like a database where everybody has all of the content of the database. And smart contracts are, as I said before, some kind of stored procedures that people can call, providing parameters to write data to the Ethereum blockchain. So it fits our use case, which is, I am a service provider. I want to write to this registry, advertising my service, saying, this is the name of my service, this is the interface for my service, and this is the endpoint that you have to call my service. This is the example of such a smart contract. I'm not going to go into every single line of code, even though it's not many, but like this works. This is full-fledged smart contract for a service registry. You can like try it on your PC, or you can deploy it to an Ethereum test network, or you could deploy it to the Ethereum main network if you want. And people are gonna be able to use it to publish their services on this contract. So it has the concept of a service registration, which has a URI, meaning like an endpoint where you can download the proto file with the definition of your service, and it has an endpoint for the service, like the IP address or the DNS name of the machine where the service is actually hosted, and exists. That's due to some intricacies of Ethereum where it's hard to figure out whether in a collection an item exists or not. So you don't have to dwell too much on it. It exposes a function which is register service. This function takes a service ID, service definition URI, and an endpoint. And this function is just going to verify whether a service by that name already exists in the registry, in the smart contract, or whether there's no service by that name, in which case, congratulations, it's yours. And you're just going to publish there the endpoint for your proto file, the endpoint for your machine, and then there's a method to get a list of services. So we talked about a URI that hosts a proto definition for a gRPC service. Where exactly are we going to host that? In a traditional centralized service platform, what people usually do is they just stick those in repos. Like you have the repository for the service, and the repository for the service holds the proto definitions to call that service. In some cases, you might have a monorepo with like 5 services and all of the proto definitions shoved into a protos directory. In other cases, you might have something more like fancy or sophisticated, meaning that you might have a web service that takes a service name and returns the definition for such a service. In our case, that doesn't work because, as we said, again, we are doing a decentralized service platform. So we need something where the service definitions are distributed peer-to-peer. Anybody needs to be able to host these service definitions. Anybody needs to be able to go fetch these service definitions. And killing the box or the server where these service definitions are hosted must not render the service inaccessible. So what are we using for that? IPFS. What is IPFS exactly? IPFS is a decentralized storage system that is peer-to-peer, works a little bit like BitTorrent, as we said, and we are going to use it to build this decentralized storage for service interfaces. So an IPFS node will be able to be used to publish these service interfaces, share them, and advertise them with the whole IPFS network. IPFS is peer-to-peer, and in the platform that I'm going to show you, both the client and the server are full-fledged IPFS nodes, so they don't need to go through some gateway or cache or proxy or whatever. Like the service and the client are going to hook into the peer-to-peer system. They're going to look for peers. They're going to advertise their contents to these peers. The peers will be able to fetch the content that is distributed by these nodes, and the peers will be able to cache the content that is distributed by these nodes. So it's going to be like a hydra where you kill a head, another one springs up. People are not going to be able to obscure the service interfaces that your platform depends on. How does getting stuff out of IPFS work? IPFS is an addressing system where you're going to hash the content of a file, and the hash of this content is going to be the address where you can find the file on the system. So any kind of file is going to produce a unique hash, meaning that if you upload something that is exactly the same as the thing that I uploaded, it doesn't matter whether it's mine or yours. It's going to be up for everybody, and it's going to be the same thing. This is an example. This is actually an HTTP gateway or proxy onto IPFS. This is the service definition, the proto-service definition that I showed you before, that I uploaded to IPFS. And that circled in red is the hash of the content of the file, which also is the address that you use to get it. So we have this distributed platform where people publish services and other people want to call services, but since it's open and everybody is participating, I don't know you, I don't want to give you free services, you have to pay me to call my APIs. How does this work? We have to implement some kind of payment system. We have to implement some kind of payment system that, in traditional systems, might be you pay me with credit card and I give you an API key, or you pay me with PayPal, doesn't matter. Again, in our case, that doesn't work because PayPal might decide that it doesn't work with you, or the bank might decide that it doesn't want your money. We need some kind of decentralized payment system that is censorship resistant and that nobody can put his name on, say this guy can use me, this guy can't. And we're going to use Bitcoin's Lightning Network. Lightning Network is a decentralized instant payment network built on top of Bitcoin that works this way. It works on the concept of state channels. State channels are essentially money that some guy commits to some other guy, and once I commit the money, you can send me invoices to pay for smaller amounts than the total. So I can open a channel with you that contains 1 Bitcoin, and then you can send me invoices for 0.0001 Bitcoins every time I want to make an API call. I pay that invoice, you verify whether the invoice is paid, and if the invoice is paid, I can make the call. Lightning Network is particularly cool because apart from being instant and because you don't have to go back to the Bitcoin blockchain to make a transaction every time you want to pay somebody. What's happening is that I commit the money and then I basically generate an authorization that I'm going to give to you to withdraw some amount of money from the channel. So I want to call your service, I'm going to give you an authorization for 0.1 Bitcoins. And then I want to call your service again, I'm going to send you an authorization to withdraw 0.2 Bitcoin, up until I reach the full amount, essentially. And if you take this authorization that I give you and you commit that to the Bitcoin blockchain, that is going to close the channel, and closing the channel essentially means that whatever balance is left there goes back to the people that put in there, and whatever was, you were authorized to withdraw, you're going to be able to withdraw. Lightning is particularly cool because it exposes a gRPC API right off the bat, so you can download the proto definitions for a Lightning Network daemon, and you're going to be able to send requests to the Lightning Network. How does this work? You can call a gRPC endpoint to ask the service to generate an invoice to call whatever method you want to call on the service. So in our example, I would be calling the horoscope service and tell it, hey, can you generate for me 1 invoice or 100 invoices to pay to use your API? and then I'm going to get the invoices, I'm going to pay these invoices, and I'm going to send requests that have the invoice number in them, and the service is going to verify whether these invoices have been paid or not. If the invoice has been paid, I'm going to get back my response. If it's not been paid, it's just going to tell me, like, you haven't paid. It's going to reject my request. So paper call is not the only method of interaction that we can do with this. You could do something where essentially a server generates you an invoice for 100 calls, and then it gives you back an API key that is valid for 100 calls, or it might generate an invoice that is however many calls you want for a month, and then it's going to give you an API key that is valid for just that. You can do whatever you want. Like, you can be creative with this. Lightning Network doesn't mandate that you have to do a paper call mode. You can use whatever system you want. So we covered a platform that has gRPC services, gRPC clients, generates the interfaces, generates the documentation, generates the client libraries to call for services to call each other, or for clients to call each other. What's the catch? There's few things. Number one is these services are still going to be hosted on centralized servers, like boxes that most probably are going to be on AWS or something. This is a problem, right? Because while the platform itself cannot be killed, if your service is problematic, somebody might decide to shut down your service. How does this get solved? Well, that's what we are working on at Ocelot Technologies, and we are trying to solve the infrastructure problem by creating this global infrastructure substrate that's going to aggregate a pool of resources from all the cloud providers and project them on top of an edge network that is going to distribute these resources to the people that essentially request them. It's powered by this decentralized nervous system that is completely autonomous and self-replicating, much like the platform that I showed you. And essentially, if somebody tries to shut it down, an error box springs up. That's it for the talk. Thank you. The platform that I told you about, this is the GitHub repo when you can see it. You can download the code, you can fork it, you can try to deploy it, you can do whatever you want with it. And I can show you how it works real quickly. This is the command that springs up a local Ethereum blockchain. Once the Ethereum blockchain is started, I can deploy the registry smart contract to the blockchain. Now the registry contract is up and running, and I can start the service. And once I start the service is going to register itself to the smart contract and publish its own proto definition to IPFS. Start the IPFS node and publish the thing. This is the service definition that the service just published itself. It's on the public internet, like you can get it yourself if you want. And now I'm going to call the service. Getting horoscope for dog, that's no zodiac sign. Getting horoscope for Taurus, day is looking great. And that's it for the demo.